It's wonderful to be here. Thanks very much for the invitation. So I'm talking today about integrating optimization constraints and control. The control bit's a little bit minor, I'll have to say, but a little bit of control within deep networks. This is joint work with a bunch of my students in Bold here, as well as some collaborators from Brian at Harvard, as well as a bunch of people in Stephen Boyd's group at Stanford. So to start off with, I want to pose an odd question for this audience, at least, which is, who's afraid of convex loss functions? And the reason why I start out with this title is that, I guess 12 years ago now, Jan LeCun at NeurIPS, I think 2007, NIPS at the time, had a talk titled, Who's Afraid of Non-Convex Loss Functions? And at the time, I think the answer was sort of everyone, right? Everyone was very much into convexity in machine learning. That was the basis for how we learn things. And Jan was a sole lone warrior fighting for the power of non-convexity in representation learning and these kinds of things. Not the sole warrior, but a lone warrior nonetheless. And this is kind of ancient history now, of course, right? Because now the tables have turned, and non-convexity is kind of everywhere in machine learning. And the default assumption in most machine learning is that you're going to work with non-convex models. You work with these deep models. These are the things that work best. And so those are sort of the tools we want to use to solve kind of to perform as well as we can on these hard problems. But at the same time, and to a certain extent, you have to sort of accept this fact, right? At least I accept this fact, right? I've kind of given up on convexity, at least for a lot of machine learning problems. And it seems to do very well, but I think there's still some sort of questions here as to what the real end game is here. Because although you have these sort of amazing domains, so I think this is really impressive. This is OpenAI's work on the Dota 2 championships. I don't really know that game very well, but it seems very hard. And they have an agent that can beat the best players in the world at Dota 2 now. And so with results like this, it frankly seems kind of, this is an amazingly complex control task, really, long time horizons, lots of potential actions, partially observable state, all this kind of stuff. And these things do amazingly well. And so the question, though, is that if we're doing this well at things, do we even need all these sort of rigor of the methods that sort of I kind of grew up with, right, that I have been using for so long? And however, I would still argue that sort of, yes, we do want to still think about more rigor in our development of such algorithms, because it's not really those domains that people are excited about when it comes to AI. What people are excited about is sort of seeing things like that and thinking, well, they therefore extend to domains like self-driving cars. Where I think that at the very least we can all agree that things like constraints and robustness and interpretability, maybe that one, but data efficiency, these things do seem all much more relevant in these high-risk, high-value domains. So what I do in a lot of my work, really, is think about how we can incorporate some of the formalisms and the constraints from traditional optimization into these new sort of models we have for learning very complex things. And that's really sort of what I think a lot of my group works on. So with that kind of as background, I'm going to talk about a few different things in this talk here that are centered around this core idea of mostly centered around this core idea of implicit layers in deep networks. Because while deep networks are thought of as being kind of very unconstrained and kind of very heuristic and just, functions that just take in an input, produce some output, there's no real constraints on what it could do, it actually is possible to incorporate a lot of constraints into deep networks. And while I think that it's one thing to use the tools from optimization and control theory to analyze existing deep networks, but another equally valid line of work, I think, is to try to inject some of the techniques from optimization, from control, into deep networks to actually make them more powerful and increase the representational power and value of these things. So that's what this talk is about. I'll talk first about sort of general notions of implicit layers in deep learning. Then I'll talk about how we can incorporate generic optimization problems effectively as layers in deep networks. And then I'll actually talk about some specializations of these two things in different cases, one on differentiable SAT solving, and then one to sort of solve combinatorial problems, and then one on an extension to learning that stable dynamical systems, nonlinear dynamical systems, again, provably stable, but using techniques from deep learning. So let's get started. And feel free to interrupt me if we have to rush through some of these. It's no big deal. The great thing about these workshop environments is that you can stop as long as you need to and ask questions. OK, so let's start talking first about structured implicit layers and deep models. Now, the way networks are typically thought about, deep networks at least, is like with a picture like this, right? So we think about there's some inputs, it goes through a bunch of junk here in the middle, and we get some output at the end. And what I want to sort of argue for is that these layers in the middle, they don't have to be as sort of generic as they're typically thought of as being. So we typically think of these things kind of as, basically matrices, matrix multiplies, followed by a ReLU operator. That's the traditional layer in a deep network, or convolutions or things like that. Very unstructured layers. They really have no constraints on the kinds of outputs they can produce. But what I want to sort of argue for is that these layers can actually be much more structured and much more complex than that, and still kind of obey the normal kind of, still be able to be integrated into deep networks. And so in particular, I've sort of made if you know sort of the work of my group, we've kind of made a business out of this, I guess you could say. We publish a lot of, you can have an optimizer here, an MPC controller, a game solver, a physics engine, whatever. And in fact, as I say, we sort of made a business out of this, and we've in fact published papers on doing one thing after another and after another. And I'm going to talk about some of these today. But the point I want to make is that there's a very common framework here for a lot of these things. So the key idea is that you want to move from thinking of a layer as kind of some sort of feed-forward, well-defined computation to thinking of a layer more in terms of an implicit definition for that layer. Right? So all these tasks, be it optimizers, be it controllers, be it physics engines, whatever, they can all basically be formulated as finding a root of some nonlinear function. Right? That's an incredibly generic thing I'm saying there, but they're basically all formulated that way, and I'll mention how a few of these are formulated, in fact, as finding roots of nonlinear functions. And so, what I would advocate for is that we start thinking about layers in neural networks, not in terms of sort of some predefined set of computations they perform, but in terms of the input and output of that layer, i.e. the x's going in and the y's coming out, those should satisfy some sort of nonlinear equation. Now we call this an implicit form layer. Yeah, Pablo.
If you draw the arrows,
yes.
Then you don't have, you have more than an implicit equation, right? You have a function.
You can have these other ones too, right? So you can embed a single layer, right? A single layer. So actually, it's like the x is not the original x, and the y is not the final output. This is just the x is going to be the input to that layer, and then the final output. You can do other transformations of that too. Is that what you're asking, or is
I'm saying why are you writing an implicit equation rather than in functional form? Why is it function?
Yeah, so of course y is in fact a function of x. The fact that the idea is you find y such that this thing is satisfied. But I want to think about it in terms of the input to the layer is the x, and then the output is some y that satisfies that thing. And I don't really care about how I solve that thing. I just care about finding a y that solves that. Of course, the output y would be a function of x, yes, and a function of theta, which are the parameters of that layer.
Yeah, then I would just object to the arrows. I mean, it's an equation at one.
There's no arrows. You mean here and here? Yeah, okay, that's fine. Sure. Yeah. I can't give up all deep learning notation, so I think of it in terms of arrows.
In control, we would say it's a behavioral.
Sure. Yeah. Yeah. Absolutely. Yes. Completely correct. Yeah. Shall we do you have a question?
Now I'm confused. I said that you want to keep the arrows because you just wanted to. I just wanted to ask whether you are just advocating for some general form of F that involves optimizers.
Yeah.
And because you think that having such a more general form is advantageous,
right,
as opposed to a parametric form that directly does the computing.
Yeah, exactly. That's what I'm advocating for. So to be clear, the y is still the input. The y is given as input to the layer. I think you're saying the same thing. I don't think there's anything different about that. I think the y, the x. You never change the x. The x is, I know, I'm confusing everyone now. The x is given, rephrase, the x is always given, it's fixed, it's input to the layer. You never adjust the x. what you do is somehow, given that x, you somehow, by some iterative procedure, by some way, we all, say a lot about that, but by some way, you find some y that satisfies that equation. And then you output that y. The y that satisfies it, that's what the output of that layer is. Now, that the form is, yes, an implicit form. I mean, maybe you don't need arrows in some sense, but it's not as if you can possibly adjust the x to the inputs. You are just adjusting the y. So maybe the arrows are not. I'm not sure if there's what the protocol there is.
So the standard network is a special case?
Yeah, standard network is special cases. It would just say that y equals a ReLU of a of x plus b, or wx plus b. That also satisfies that y minus wx plus b is a ReLU of wx plus b equals 0. But this is a much more general form.
So you're intentionally allowing y to take multiple values?
Actually, I'm not going to worry about so I'm going to, for the most part, at least in this form here, ignore issues of existence and uniqueness. I apologize for that because those are huge issues. Most of the cases we define here, it will be unique, and it will exist and be unique. We have some other work, but that's not actually guaranteed. But I'm going to assume it exists and is unique here. Yeah, but that's actually not. The point is less about existence and uniqueness and more about the representational power that this has over just simple feed-forward functions. Okay, so a big question now is, with this formalism, deep learning is based all on backpropagation, right? So deep learning, the whole idea is you take your output, and I basically backprop some error of my output through the whole network to adjust the parameters of the network. Right? That's sort of the. I agree that's actually probably like the one defining characteristic of all deep learning is it seems to be gradient based. Other than that, everyone what you want to call deep learning almost doesn't matter. So how do you compute Jacobians through this layer? I'll put it like this. And this actually seemed, people thought this, I think people didn't realize how simple this was, honestly, for a while. It's sort of the things you learned in high school calculus here. It's just implicit differentiation. So we know that how do I differentiate y, the output of this layer, with respect to something? It could be either the inputted layer x, it could be some parameters of the network, it can be anything. Right? How do you do that? So this is actually extremely easy. You just apply implicit differentiation to this. You differentiate both sides with respect to whatever the quantity you want. You apply the chain rule to that, right? So you have the derivative of the first term, which is just this thing, and this thing here, y is a fixed value, no longer it's no longer a function of whatever differentiation with respect to. That you can compute with an automatic differentiation toolkit. Plus, now you just apply the chain rule here. You have this thing with respect to the partial derivative with respect to y times the derivative of y with respect to this thing here equals 0. And now to find the thing you care about, you just rearrange this equation to get this thing equals this inverse times that, negative this inverse times that. And this is the implicit function theorem. This goes back decades, if not centuries, in calculus. It's very, very easy, but it's very, very powerful as a paradigm for differentiating through these implicit layers. Because importantly, here's what the main point that I'm making here. The main point I want to make is that I am not advocating trying to construct some method that solves that fixed point and then unrolling that and then backpropping through that. That's kind of what people traditionally did in deep learning, right? If you wanted to solve something, you would write a procedure, and you would sort of then, that's a computation graph, and you can then backprop through it, and that sort of works. I actually don't want to advocate for that, because it's very memory intensive. You have to store every single intermediate computation in your iterative procedure. It also creates very long graphs, which tends to sometimes cause numerical issues. So you actually can have things blow up as you do this. Instead, what I'm arguing for is that outside of any autograd framework, autodiff framework, I shouldn't say the word autograd, outside of any automatic differentiation framework, you just find the exact solution using whatever method you want, and then you use this implicit function theorem to compute the solution somehow. Okay? And this is a simple idea, but it's actually quite powerful in the context of deep networks, and it allows us to do a lot of, I think, very cool things with these networks that were traditionally not thought of as kind of being inside the domain of deep learning. So the rest of the talk is going to be really examples of a few different examples of this, a few different cases where we've taken this idea and applied it to, I think, accomplish some very, maybe not from a real applied standpoint yet, but applied it to accomplish some very cool things, at least algorithmically.
Is it just the fact that it's more compact?
So I think, yes, there's a few things. I think it's more compact, but it also lets us express things, structured layers that we normally wouldn't be able to express in deep learning. So I'll give an example in a second, but you normally don't think of a deep network as being able to enforce hard constraints on its output, right? You think of it as being sort of, I can train it to minimize some loss function that maybe penalizes those constraints, but I don't typically think of it as, really satisfying hard constraints. But with this framework, you can, in fact, make networks satisfy hard constraints on their output. And that's a very sort of powerful paradigm that I think it needs to be explored more in deep learning, because people don't typically think about that. Yeah?
What are the issues of numerical instability and computation still persist with the inverse?
Yeah, that's a good question. So how do you compute this inverse? The answer is you don't typically compute it exactly. Typically, you have some iterative procedure for computing this solution of the fixed point. And while I'm not going to actually really get into this too much, the reality is that almost any time you can define a forward procedure, that almost always will define a corresponding backward procedure for solving this inverse equation. One thing that's important to note, though, is that this backwards equation is always a linear equation, right? Even though this is nonlinear to start with, this is always a linear system, because it's just a first-order derivative, so it's always linear. And that's very powerful. So usually it means that iterative methods to find this one are actually faster than they are to find the forward solution. That's not a hard and fast rule, but it usually works out that way. OK, so with that being said, let me jump to our first real example here, which is incorporating optimization as a layer in deep networks. So what we're going to do here is we're going to embed a layer which says the output y is the argmin over z in some set, and the set can be defined by the inputs to the layer. So we can use the inputs to define what that feasible set is. Some joint function of this optimization variable z and the input to the layer x. So we're going to solve that. And this allows for some very expressive functions and constraints. Sort of as you were saying, right? It's not just that we can, it's more compact here, which it is more compact, by the way. You can represent things that would take exponential numbers of hidden units represent with a typical network. You could do it with a linear number here. But more importantly, I think it just lets us specify things in a very intuitive manner, right? It kind of lets us specify very intuitive constraints and requirements we have on the different layers here. Maybe you only have one on the output, so it's only on the output layer. But this is a very powerful notion within deep networks. It's not that well explored. It lets us put a lot of bias into our network. So how do we do this? How do we actually compute a layer where the solution is the argmin of the input, and how do we differentiate through that? Well, this is exactly actually the setting we saw before. This is exactly some sort of fixed point condition, or from some sort of zero, finding a zero of some nonlinear equation. In particular, we can take a very sort of generic form of convex optimization, like cone programming. So we want to minimize, a linear form to some cone constraint, and with proper cones with enough complexity there, you can represent very complex programs with that framework. And solving this problem, of course, is equivalent to finding a zero of certain operators. I mean, there's actually a huge number of ways you can formulate this. One way, this is called, I think, the Minty parameterization. It's a certain sort of projection operation combined with a linear term. And if you find a zero of this thing, you actually have a primal dual solution to the original problem. So that's sort of a nice thing. And here's the form of it. Doesn't really matter. This is the form used by a lot of solvers internally. But the point here is that this thing, with those two definitions there, is exactly just some nonlinear function of our input. In this case, u, again, is sort of a variable that encodes both z and any other terms. And our matrix, our problem data here, which is C, A, and B, is all encoded in Q here. But importantly, C, A, and B can all be functions of the input to the network, right? And so the question is, with this framework, or not the question, but the point is, and I won't get into the details too much here, the point is that we can differentiate this thing to be able to get using the exact implicit function there I described before, to be able to compute the needed derivatives of our optimal solution, z star, with respect to the problem data as well as the input, if the input is what defines the problem data. Right? And so without getting into any details, that's sort of the high-level picture there. It's fairly straightforward. You end up having, I actually don't even care how you solve the forward problem. You can solve this any way you want, with an interior point method, with a first-order method, however you want. That will typically give you a corresponding way to solve that inverse that you want to in the backward pass, but you have a way of computing these derivatives just using that implicit function theorem.
There's a lot of non-smoothness here, right? So
Yeah.
Do you have clever ways of taking sub-derivatives?
Yes, you do. So there is some details there. It isn't too bad here for some cones. So for some cones, this isn't too bad, right? The projection is still differentiable. So for the positive orthant, that's just basically a clipping function. You can take the derivative of these projections, and they sort of still work out okay. But there are some details, yes, to get that to be smooth. But when these are sort of the right kinds of operators, that you can derive a corresponding backward pass that does in fact solve it. Yeah. Yeah. Okay, so that's all I'm going to say about the mathematical form there. But what I'll say more sort of from a practical standpoint, we worked on stuff like this, actually not in the cone form, but we worked on stuff like this for quadratic programs a few years ago. And while I think being a very kind of nice idea, it never really got that much uptake by the broad kind of community of people doing deep learning. Frankly, because they don't really work in optimization, and they don't really know how to take some problem and formulate it as a cone problem, say, right? We've given up doing this a long time ago kind of ourselves, but we were making people go back to formulating kind of cone programs. So a big challenge with this is it's very hard to formulate these things. And so what we have in normal optimizations, we have these libraries, and CVXPy is one of them written by Stephen Boyd's group. I know there are many others that people also use. Basically what they do is they let us, from a coding standpoint, write these optimization problems much more efficiently, right? So if you have a problem like I want to minimize over x, say some L1 norm of ax minus b subject to a non-activity constraint. Everyone knows you could write this as a linear program, right? It's easy to do, but it's kind of a pain. You have to figure out, okay, so what are the slack variables? What are my bounds? How do I? If you really want to put it in matrix form, you have to structure these silly block matrices that just easy to write on paper, but it's actually there's a lot of errors you can make when you code it up. And so instead, what we do is we use libraries like CVXPy to write this in a very readable form, right? We have a variable, we have two parameters, we have some constraints, and our objective is to minimize I don't know why they have the 0.5 here. Ignore that. Minimize something, and then you basically create a problem in CVXPy, and magically, by the magic of these graph transforms of that CVXPy does, it basically converts it to a standard form cone program. And so what we've done in this recent work here, and this is work that we did that came out this last year at NeurIPS, is that we did the same thing for the differentiable case. We basically built a differentiable version of CVXPy. And so here's how it works. It's actually quite simple. So this is, as I said, this is a collaboration with Stephen Boyd's group at Stanford. And what we did is we basically took each stage of the conversion of this sort of procedural conversion from code to cone program to solution, and we made each of those differentiable, and actually maybe more importantly, sort of pluggable into standard toolkits for deep learning. So this basic process is, the way that CVXPy works to a certain extent is you take, your inputs to the thing, so these are your variables, you take your parameters, it performs a canonicalization of this thing. So it canonicalizes the problem into cone form, it generates these CAB, then you generate a cone solver, it sets the output, and then you extract the solution, and you get Y. And the important sort of elements here was that in order to do this, we had to make sure that these two elements were linear. So in particular, linear in sort of how you would transform parameters of the problem into these elements here. But once you do that, the process is very simple, right? You can easily differentiate through this thing because we just told you how to differentiate through the cone solver. That's kind of annoying and non-smooth. That's not that hard. The other two are really easy. The other two are just linear transformations. So it's sort of Pythonic, and you have to sort of trace down these trees to do it. But it's actually quite easy to do conceptually. It's just a linear transform from problem parameters to these matrices here, and then a linear extraction of this. So all elements of this process can be differentiated through. And in some sense, I mean, that's great, but what I'm actually sort of most excited about is just how easy this is to use in practice. So I don't know if people here have played much with PyTorch, but if you play with CVXPy, hopefully you'll be able to see this is actually just as easy as sort of writing a CVXPy problem is now integrating a CVXPy problem into a library, a neural network library like PyTorch. So all you do is you take, I guess, the same code I had up there a few times ago. You take your problem and you create a layer from it where you pass in certain things as parameters and certain things as variables. And then the parameters are the things you can differentiate with respect to, and the variables are the things you optimize over. Right? So I can define, PyTorch variables now that are my two parameters here. I can solve. Given those sets of those parameters, I can get a solution from that. And then I can, just like as you do with any other problem in CVX or in PyTorch, you can compute gradients with respect to these parameters of the solution of the argmin of the solution to the optimization problem. And our hope, at least, is that this, and it's starting to actually. I think people are starting to pick this up a lot more than our past stuff. It's starting to sort of make this an easy process where you can now do, essentially, it's basically simple cases would just be simple sort of bi-level optimization, right? Where you want to optimize some sort of an optimization procedure such that the solution of that optimization procedure produces something that you want. You can do this very easily with kind of frameworks like this. And I think that's sort of a very sort of powerful notion that has not been explored. You can, of course, also hook it up with more things in PyTorch. You can put convolutional layers, all that kind of stuff into it as well. But you can also just sort of use it as a way of differentiating through the parameters of an optimization problem to give you certain solutions. So as a simple example of this, one example that we just used as a demo more than anything else was data poisoning examples. This is actually not a deep network in any real sense. This is much more just like a bi-level optimization problem. But the idea is, if I have a linear machine learning algorithm, now a convex one, that fits data by minimizing some regularized, oops, I even left out the norm there, by some regularized risk minimization problem, I can define my optimal parameters here as the defined by basically the data set that they're given to it. These parameters are the solution of the argmin of the loss plus some regularization term. And then a common problem that people look at in machine learning and sort of adversarial machine learning is to say, if I have some other data set that I want to evaluate my function on, i.e. a test set or a validation set, how much can I perturb my original parameters, or sort of my original data points, such that I would sort of maximize the error on this new test set? And what's very nice here is that with a few lines of code, you can basically do this very easily. You can compute gradients with respect to all your input points in your original data. This figure here shows the training points as well as their directional derivatives computed sort of instantaneously. Not instantaneously, sorry, I shouldn't say that. Computed very quickly. The training points with all their directional derivatives. And importantly, this shows the derivative of the test loss function with respect to perturbations of those input images. So it lets us very easily compute kind of adversarial manipulations, data poisoning essentially, manipulations of this data set in a way that actually lets us sort of figure out how to maximally kind of increase our test loss. So this is not a full deep learning example, to be clear. This is sort of a demonstration of it. But I think even there, it gets to sort of the power of this thing is kind of coming through, right? Because you can just solve this kind of thing with gradient descent then. You're basically solving a bi-level optimization problem where the outer loop you're using gradient descent and the inner loop you're using CVXPy. And you don't have to really worry about how you do this. You just sort of let the frameworks handle most of it. It's a few lines of Python code to do all this. So I think that's sort of a very powerful paradigm, and I think it's really, hopefully, going to increase the proliferation of people integrating constraints into deep networks. I'll mention a few more. So that's all I have to say about this sort of general case. This is a very powerful paradigm, but I will, and it's great for prototyping. I will say that just like CVXPy, which is also great for prototyping, it's not, if you have a very particular problem you want to solve, it's probably not your best way of solving it, right? You probably want a more specialized solver that can actually solve these things in a more well-defined way. And so actually, the next two elements I'm going to talk about are different ways of solving specific instances of optimization problems for specific purposes. So they actually both fit into this framework, but we're going to have much faster, and in this sense almost closed form, but for this case it's at least much faster, solutions that let us solve these problems much more quickly. Any questions before I keep going, though? I guess people have been asking them, too. No one would, no one would hesitate. OK. So next up, differentiable SAT solving. So this is all very cool. We're differentiating through optimization problems, but it sort of is leaving out a whole class of problems, namely discrete problems, or problems with any kind of switching structure. Even LPs are not that differentiable, right? Because they actually sort of switch. They, depending if you try to differentiate an LP with respect to the objective, you'd get nothing because most of the time the solution doesn't change when you change the objective a little bit. So there are all these sort of discrete problems that, while you can compute the derivative for them, it's not going to be very informative because it is going to be basically 0 everywhere. You're going to say, OK, if I change my problem a little bit, my problem data, my solution does not change, in fact. And so the question is, can we use these techniques to actually still address problems like that? And I think that for a broad sense, the answer is still very much up in the air. But I think there are classes where we're kind of understanding a little bit about how to do this. So one example of this that we've done, that worked on, is using higher order relaxations, in particular semi-definite relaxations, to sort of smooth out combinatorial problems and make them more suitable for inclusion in differentiable architectures. I think it's actually a very cool sort of general idea because these things are easier to solve sometimes because they are smoother than the underlying problem. And smoothness is exactly what we need, not just for solving them, but also for differentiating through and getting back meaningful gradients through these problems. Andreas has some related work to this with a very different approach for doing that, using submodular minimization and maximization in different cases. But we're going to look at kind of a semi-definite relaxation type approach for this. So what we do here is actually quite simple. So we're gonna base our framework on the MAXSAT problem, which is the optimization variant of SAT solving, right? So it's not just is this clause satisfiable or not? It's of the set of clauses, how many of them can we satisfy? So basically, you can choose some d-dimensional binary variables, such that you want to satisfy as many of these clauses as possible, where S here is a sign matrix, so S is -1, 0, or 1, depending on whether or not that variable is in the clause and if it's negated or not. And you basically want to make as many of these clauses satisfied, i.e. have one variable that is, in this case, one variable that's satisfied. So that's the problem we're going to look at as our canonical kind of combinatorial optimization problem. And it turns out there's also a very, very well-known semi-definite relaxation of this problem. You basically look at the simple sort of outer product of your binary variables, and you just minimize a quadratic form of this, subject to the constraint that the diagonal entries are equal to 1. It basically corresponds just to sort of the vector lifting of these -1, +1 variables to like the unit hypersphere. So that's sort of great, and we could at this point actually just do this and plug this thing in to our CVXPy layers library and get a differentiable SAT solver that way. But it's not really practical to do it that way because these things are quite slow, right? If you solve it as an SDP, it is quite slow, and it's not really the best way of doing things. Fortunately, there are some much faster ways of solving this particular SDP than just using a generic interior point method. One of these, which we've worked on a lot, is basically the Buer-Monteiro method. It's essentially you factorize x into its low rank form. And in our case, for this particular problem, you can actually do more than just then do gradient descent on it. You can actually come up with a closed form block coordinate descent solution for these things. You basically iteratively compute each VI, each sort of vector relaxation of the binary variables as some normalized version of some function of the other variables. And you just iterate this thing. It's a very simple one-line method, and it will converge nicely. In fact, it was sort of proven by us, but some others as well. It will converge actually as long as you have sufficient rank in this thing. It will converge to the global optima of the SDP. This is actually a sort of a very long line of work that proved the necessary steps to show this. But once you have all that past work showing it for this case, just takes a little bit of work at looking at the Jacobians of this structure here. And very nicely, this is an algorithmic procedure for finding the SDP solution, but it's also a set of fixed point equations that are satisfied at the solution. So to actually differentiate through this thing, you don't use the sort of SDP itself, you actually use the equality here, with equality, because at the solution, this fixed point iteration is stable. So you use that as the fixed point condition, as the nonlinear function you want to solve. You differentiate through that, and you get a very, very efficient backward pass that essentially mirrors exactly the forward pass. SI, right, so sorry, did I say SI? Okay, yeah, so Sij is the clause matrix. So that is the jth variable in the ith clause. And Si is sort of the vector of the whole ith clause. Yeah, so the parameters theta here would essentially correspond to the clause matrix. So what we are learning in some sense is a clause matrix. Now, to be clear, the clause matrix for a normal SAT relaxation is always -1, 0, or +1. For the SDP, it does not need to be -1, +1, and 0. It can be actually anything you want. It's a continuous parameter. So you actually learn an arbitrary value of this S matrix as your parameters physically of that layer. That's what the parameters of the layer are, is this clause matrix. And there are lots of tricks here. Like you have to learn a low rank form of it to regularize properly. There are a lot of things you need to sort of do this well, but that's the basic idea. We actually don't encourage sparsity. That we didn't end up doing. To make it more like a real clause matrix, we just sort of let it be as dense as it wants to be, but low rank. Yeah?
What was the assumption that you made on the relation between the relaxation and the true solution?
Yeah. Yeah, so maybe I actually go say this. So you're absolutely right that in general, these are loose relaxations, right? I mean, this is not this is not going to give you exact solutions to the MAXSAT problem. It's going to be approximate. So here I'm going to be a little bit hand wavy, because I think that I actually am not going to be too strict here. What I'll say is that the ultimate goal of a lot of these things is not really to solve a given MAXSAT problem, right? It's to use a combinatorial optimizer somehow within some larger sort of system. And as long as you can train the parameters, i.e. the clause matrix, to give you a good solution for whatever problem you want to solve, it's sort of okay if the thing is loose. Now, there are some additional steps here, though. So obviously, the MAXSAT layer is operating over this vector space, or over this SDP space, which you don't really care about in the end, right? I want solutions. I want binary solutions to my actual task that I want to solve. Otherwise, it's not combinatorial. So what we do in practice is that we have some inputs to the layer. Those typically end up being some subset of the values that are fixed of the V's. We then expand them, project them out into a higher dimensional space. We solve the SDP relaxation. We run from that we get the relaxed outputs, and then we run randomized rounding to round those back to be 0, 1 assignments. In some cases, we can use the actual probabilities of the randomized assignments. In some cases, we actually use samples from that randomized rounding procedure. But you can do both in both cases. So at a high level, the input to the layer is some discrete set of partial assignments, and the output is kind of the rest of the assignments filled in somehow.
So I would interpret it as the assumption is that the solution space is pretty wide open, and that there's a very large number of solutions. The chances are that if you do the last step of sampling, you will hit a solution.
Yeah, I think that's fair, yeah.
Because if you have an over-constraint, no solutions, you can still run it and you'll get no solutions.
Yes.
And if you have very few solutions, so somewhere in the middle you have this spike of, then it's just going to...
Yeah, so this is about like the phase transition of what's going to happen now. Yeah, so what I would say is, yes, I think you can take it. So if you really care about solving the MAXSAT problem fundamentally, then I think you're right. I mean, MAXSAT is also, it's sort of easier because it's not SAT, so you don't have to go to the phase transition. It's just that you can't find a fully satisfying solution or not. So you'll find one that when you relax it does not satisfy all the clauses, because remember, it is sort of the max version of it, not the SAT version. I think you can debate whether that like how much that really matters, because again, at the high level, you are just trying to solve, okay, to a certain extent. You're not really trying to solve a well-defined problem ahead of time. You're actually trying to kind of learn the problem in some sense to fit some input-output mapping that you observe, that you want to fit with the function. And the real argument I'll make here is that this functional form is much richer than you get in a lot of other deep networks that lets you learn things that are very hard for deep networks to learn. But yeah, I think if you think about solving the actual MAXSAT problem, you're right. Is that this would only work if the solution, if the problem is way under constrained and you can find many solutions. Yeah.
You round at the end, you lose the gradients again.
Yeah. So how do you do? So there's a way to get through rounding, right? There's all these what are they called? Like the Gumbel softmax kind of stuff, right? To get things through rounding. What we typically do, for the most cases, we actually use the rounding assignment. So we use that the cosine of the truth vector and the inverse cosine of the truth vector and the variable as the actual thing that we're going to propagate through. And then at inference time, when we actually want to run inference, then we do hard assignments there. But when we're training, we use the soft assignments for that exact reason, that discrete sampling, you can do it, but it doesn't really work. Okay, so what can we do with this? We can do some cool things with this. So one thing we can do is learn some things that are surprisingly hard to learn for deep networks. So deep networks, for example, are very bad at learning the parity function. So if you give it a string of bits and apply like a recurrent network to this, where the only supervision they have, they see a string of bits, and the only supervision they have at the very end is they say it's a 0 or a 1, depending on the parity of that string. That's a hard thing for a normal recurrent network to learn because the supervision is very sparse. And despite a lot of it can do it for many short sequences, but if you have like a size 40 string, it can be quite hard to learn a function like the parity function. So it's just an XOR, right? You just be applying an XOR to each element there. And all I'm saying here is that maybe it's sort of trivial because it's not very hard. It's sort of a very small number of parameters. But with this procedure, you can learn functions like a recurrent structure that encodes the XOR function, and you can learn that from data. So actually, given just single bit supervision, you can learn an XOR function. Yeah.
Is this XOR of a random subset?
It is a simple machine learning problem. So it's XOR the whole thing.
Oh.
Yeah.
Can you try XOR
So-
of a random subset?
XOR, it doesn't know. That would be it wouldn't learn that. That would be very hard. Because then you have to sort of have a flag of whether each one is included in that XOR or not. Which maybe it could learn actually. But we're just learning a single recurrent structure which can be applied to as long a sequence as you want. And so it's just learning the XOR function basically. But with single bit supervision only at the very end. So that's hard for a normal network sort of backprop through. You basically all your gradients go away. You get nothing meaningful. But this can do it. Yeah.
Do you have a setup so that you can kind of plug in this type of problem into a larger, say, deep neural network?
Yeah. I'll get that at the end. I'll have a silly example that everyone will laugh at, and everyone always laughs at these. But we do have an example where right. So I should really clarify. All these examples I've shown so far, there's no real deep learning here, right? I'm talking about deep learning, and I'm making differentiable layers, but I'm basically using them as a single layer to learn something. This is a recurrent structure, so there's a little bit of sort of this, but you absolutely can are you talking about like plugging them into like a convolutional structure here, and then you have some discrete structure, and you do that. So I will give an example of that at the end. And yes, you can. Yeah. Some other cool things you can do are do things like learn Sudoku problems from examples. So to be clear, solving Sudoku is easy. No one has a hard time with that. Even I have a hard time with that, for hard ones. But linear programming and semi-different programming does not have a hard time with it. But what's cool here is that given a relatively small number of examples, so this is in case, we just gave it 10,000, which is small for as far as deep learning goes. 10,000 examples basically of a board, a one-hot encoding of this board. So there's, for each square you have 9 possible entries. The ones that are not filled in are all zeros. And then you're given the input with some missing entries and the output filled in. So it's told nothing about the rules of the game. It's told nothing about how to actually play this. It's just given input-output mappings, sort of map from observation to the solution you want filled in. And doing this, we're actually able, and with a relatively small number of samples, and with enough data, a deep network can learn this too, but it takes like 1 million samples or so. But with a much smaller number, it's able to sort of use the encoding that is solving a logical structure underneath it to learn how to play Sudoku. So basically, after 10,000 examples, we learn more or less, our test set performance, and that's test set meaning that we have to get every single element right on a new puzzle. To get it right here, it gets not quite 100%, but basically very close to 100% just from sort of observing past examples of Sudoku being filled in. And the point here is that not that this is a hard task. You shouldn't solve Sudoku like this. You're getting not quite perfect accuracy here. But this is a problem that's very hard for most networks to solve, precisely because they have a hard time encoding global structure in the output, right? So networks are really good at sort of doing local identification. They're very bad at incorporating things like, that the 1 is here, so it can't be here. So it's here, so it can't be here as well. It's been traditionally very hard for networks to capture, and by embedding this sort of very little, I mean, all we're giving it really the examples and sort of a blank clause matrix. We don't tell it anything about the rules, but through gradient signals, and this SDP relaxation is actually able to sort of tune this clause matrix in order to solve the Sudoku problem. But a common question, by the way, is that does it learn the actual rules of Sudoku? And the answer is no. It learns a random, I mean, first of all, these things can be, you can have arbitrary combinations of the things and it's still a valid clause matrix, so it's very hard to know for sure. But my impression is no, it's not even learning a valid clause matrix. It's learning something that kind of captures some of the elements, but still gets it wrong a couple times. What's even maybe nicer here is that not only can you solve that, you can also permute the entries randomly, and it still works just as well, right? Because it doesn't know anything about the local area, whereas, and this is actually impossible for humans to solve, right? People couldn't take a Sudoku puzzle and have it all permuted and still learn it. So you permute the rows and columns in some fixed way over all puzzles. Humans, I couldn't do that, right? There was no way I could solve that. But because, I mean, it's the exact same process here, it's able to learn it in the exact same way. Even ConvNets can't do this because there's no local structure there anymore. So they actually even fail. I mean, you can make them overfit if you have quite enough of them, of a big enough one, but then you still get 0 test performance. And the same size ones can't even overfit. They can't even fit this function at all. And then finally, maybe to get to your point before, we're also deep learning people, so we have to run some experiment with MNIST digits. So what we did is we created a Sudoku task of an MNIST Sudoku task. It's very conveniently 10 MNIST digits. So basically give it as input grids where each input was not a digit, not one-hot encoding, but actually a picture of a digit from the MNIST data set. And it is a silly toy task. Yes, it is. But what we do here, right, is we have this is our input. We run a convolutional network on each of these digits, and we do it individually. So we do give it the same convnet applied to each digit individually to create some encoding at the end here. We fit that encoding, not required to be the one-hot encoding, but some encoding. We fit that encoding into SatNet, and we suffer a loss in the end. And this process, backprop through end-to-end, actually does learn to play Sudoku. Not as well as the other case, because you have to also learn to classify MNIST digits while you're at it here. But it works pretty well. It works pretty well for sort of solving this problem and learning to play Sudoku, visual Sudoku. It's still a far cry from the real thing you would like, which is just take a picture of a Sudoku board and learn that entire thing end to end. But it's still nonetheless kind of cool. Okay. So I don't have too much more time here. Let me just give one more example. Yeah, question.
One thing I'm a little confused about is the level of problem-specific tuning that's needed.
Yeah.
In order to say, determine what your SatNet portion needs to look like.
Yeah. So here they were very generic. So it was basically just nothing. It was a blank matrix, blank clause matrix that we sort of initialize randomly and then tune with gradient descent. The one thing you have to vary for problems, though, is essentially the rank of this clause matrix. So that does really matter. It can be arbitrarily big, right? And what's the rank? So S is itself. I mean, you get an S transpose S term, but you also want S itself to be low rank, and you also actually add more additional variables. So you have these gadget variables, right? That actually are additional variables that are not given by the input of the problem. They're sort of assigned freely, and you often have those as well. So it is your outputs are not just the variables here. They're also additional variables you add to the problem to that can increase representational power basically. And so this that does require some tuning. And I think we still don't have a great sense of exactly when it's going to work, when it's going to not work. But my students are getting good at tuning these things to work on the right problems. So I'll say it's still somewhat of a fine art because again, the outer problem is still super, incredibly non-convex, has all the same problems, maybe even worse than normal deep learning, because we're the only ones, working on it. You don't have a whole community even working on it, but it's still doable, right? But it does take some. There are heuristics still. Yeah.
Can you say a word about chaining multiple layers like that?
Like this, like multiple SatNet layers or something like this. Yeah, we haven't done. I mean, so we don't have examples of that yet. It's certainly possible. What I will say is that empirically, these things seem even harder to learn with outer optimization than normal deep networks, as you would expect, because they have more local optima, right? There's more invariances there. And so I don't really try to mess with like chaining many sat nets together, except in that recurrent structure where they're all weight tied together. That's maybe one exception. All right, so maybe let me really briefly just say one more thing, and then we'll be done. We've had questions for that, so we can leave for lunch. I'll try to finish by 12:30. Okay, so the last example I want to give is an example which is this is honestly just like a little trick, if anything else, but on learning stable dynamical systems. So maybe finally getting back to something a little bit more relevant to control that might be of interest to people here. Well, additional interest to people here. So we're going to consider the problem of learning continuous time dynamical systems here. So just some dynamics here, where we want to ensure that f is globally asymptotically stable around the point x equals 0. And the reason why I sort of like this problem is it's actually non-convex even for linear dynamics and a quadratic Lyapunov function, right? You can't learn them simultaneously at the same time. Given one, you can learn the other, and given one, you can learn the other. But for a linear system, it's actually hard, right, to fit a linear system of data that is guaranteed to be stable. Right? The set of all stable matrices systems is not convex set, so it's hard to optimize over that set. So how on earth could you do this if you're talking about a non-convex, non-linear system now? And so here's sort of where I like, again, sort of see some of this power of simple constraints and simple optimization constraints manifest in a deep learning system. So what we're going to do is just kind of, it's basically cheating, I would say. We know that f is globally exponentially stable if there's a Lyapunov function that proves it's stable, right? So the inner product of the derivative Lyapunov function and f, which is the time derivative of the Lyapunov function, is always less than the value of the Lyapunov function by some constant. That will guarantee global exponential stability if you can satisfy this. So what we're going to do is we're going to learn f that just forces this thing to always be the case. And in particular, I'm going to jointly learn f and the Lyapunov function, v. They're both going to be neural networks, such that I don't really learn, I don't parameterize f sort of natively. What I do is I learn some other kind of nominal dynamics g, and I just project g onto the set of things that are decreasing on that Lyapunov function, right? It's the simplest possible thing you can do. But we know how to do projections like this now, right? This is a convex problem. In fact, it's actually projected into a half space, so it's even easier. There's an analytic form for this, right? So you can just actually write it as like a ReLU operator that just, if I optimize this over g, for any g and any v here, this will be a stable system, globally stable system. And so I can just do things like fit both g and v to data using automatic differentiation to compute all my needed derivatives here. So this is a sort of a trick, and I won't spend too much time on it because it's a simple idea, but it's kind of cool. I like this idea because it basically means that we can learn globally asymptotically stable systems using deep networks. Yeah?
You know the catch that this has to work at every x?
Yeah, it has to be at every x, but the point is I'm defining my f so that this holds at every x. Right? I'm just defining f to say, give me whatever my network gives me g, then project it to enforce it.
The Lyapunov function gives you a parameterization.
Yes. The parameterization here can only encode globally stable systems. Now, there are some catches here. Actually, is that the next slide? Yeah, there's some catches here. So, for example, you see a term that like divides by v here, right? So v has to be unimodal. And it has to only have one minimum at x equals 0, and it has to be differentiable everywhere, right? So otherwise, that thing's going to be undefined.
This is some closed condition.
What was that?
Should go.
Yeah. So it has to be both. It has to have both. It has to have both be upper bounded by a quadratic function and lower bounded by a quadratic function. But if you have those two, and its derivatives also have to be upper bounded and lower bounded by a quadratic function. But if you have those things, then you can do it. And it actually is not that hard to write a function that has that. Yeah, question?
That condition, I think, is guaranteed just by exponential stability.
What was that?
I think the exponential stability of the system guarantees that condition is satisfied.
Well, it depends. But it depends on the functional forms of g and v, right? So for v?
For v, there's a theorem that shows exponential stability guarantees that your v is going to be between 1
Right, but I want to create a V such that we are exponentially stable. So
you were assuming it was already.
no. I'm trying to parameterize a set of all networks that are, by definition, exponentially stable. So they have to satisfy the condition in order to guarantee exponential stability then, yes. They have to be both upper bounded by a quadratic, lower bounded by a quadratic, have the gradients that are also bounded by the norm of the vector, yeah. With upper and lower bounds too for that. So there's a little bit of subtlety here, but it turns out, so G is arbitrary. G can be whatever you want. It can just be any arbitrary deep network. It has to be smooth, but as long as it's smooth, it can be any arbitrary network. V is a little trickier. V has to be, as I say, unimodal, have its minimum at 0, only one minimum at 0, has to be positive definite, right, and all these things. So that's a little harder, and it's hard to, it is actually hard to specify the set of all, specify a neural network that can capture all those things. But it turns out you can actually do a pretty good job of this by using what's called an input convex neural network to represent V. So it's actually very easy to write neural networks that are convex functions of their inputs. If you think of a neural network as a bunch of sort of iterated, it's like a normal neural network now, not one of our fancy ones. All that's required here is that all the layers, so the activations have to be monotonic and convex themselves. ReLUs do that. You make a smooth version of ReLUs be differentiable. And later layers, the weights here have to be positive. Because then, the function is positive combinations of convex functions. You're applying a convex function to those. Everything stays convex. And so you have an arbitrary, again, by definition, these functions are going to be convex. And here and then you basically shift it to be 0 at 0, and you add a little hinge term there to make it to satisfy the theory. So this parameterization satisfies what we need from it. And you can prove that with this parameterization, any weights I choose, no matter what I choose for W, W2, for the parameters for G, whatever, you'll only have stable systems by definition. And then you can optimize those parameters to fit whatever data you want while being guaranteed that your fitted function will still be globally stable.
I don't understand what sigma and h is.
Okay, right. So sigma here is the activation function. It's smooth. It just has to be a smooth monotonic function.
That somehow heuristically.
Yeah, that's basically is a smooth version of the ReLU operator. So the ReLU is normally just like a max of 0 and that. It's just like a Huber kind of ReLU, basically.
Okay, and then h?
H is defined as the network. So H here is just the network, yeah. Yeah.
Okay.
So with this thing, everything is stable. And here's what it looks like. So here's a random weight. I just pick a random weight, right? Here's my G, when I randomly initialize G. Here I pick a random Lyapunov function, V. Random weights, again, you get functions that are guaranteed to be convex and 0 at 0. And here's what your dynamics look like when you combine the two things. So these capture pretty complex dynamics. It's just 2D. You capture these pretty complex dynamics. But you are guaranteed, no matter what weights I pick, they're guaranteed to be stable. And that's a very general function. And so I'm running out of time here. So what I'll just say is that you can do cool things with this. Like you can learn multi-link pendulums, which, by the way, we cannot predict them over long periods of time. They're chaotic systems. You can't forecast them. But they're OK locally. And if you fit a normal neural network to a multi-link pendulum and then simulate that forward, it will blow up instantly, right? Because they are chaotic systems. You will get systems that diverge. And as you increase the number of links, basically your error will just blow up. Here, our error is 0 after this time step. That's just because you've settled, right? You've settled to the 0. It's a damped pendulum, so you've settled to 0. But here, it's not that accurate, right? It's not that accurate in the meantime. There actually is a little time where it goes up then. But you're basically able to learn these systems that capture complex nonlinear behavior, while still guaranteeing global stability of the system. So if you simulate it forward a long time, it probably won't be accurate, over medium horizon, but it'll be pretty good over you're guaranteed it sort of won't blow up. Maybe even more relevant, because that's a little bit of a weird example, are things like learning dynamics over latent spaces in generative models. So here we actually looked to learn dynamics that would capture like these video textures for like a fire image. So we used something like a VAE, a variational autoencoder, to encode basically the latent state of like a 3-dimensional state for these images of fire. If you learn dynamics of this normally, you'll basically, you're hopeless. You will have dynamics that sort of diverge to infinity, and you basically, your model converges more or less just to some static image that it will output forever. if you use our models, you get interesting trajectories in latent space, and you get interesting, illustrations of the dynamics for the system. Okay, so that's all I have. I sort of describe this as kind of like the zen of abandoning outer loop convexity. So I think that, so maybe let's just give me one more minute here. The techniques that we sort of use in optimization and stability control, I think the common mindset people have is that we're going to use those tools to analyze deep networks as they currently exist. Right? We're going to take deep networks and somehow convexify them or look at their stability properties or something like that. And that's a great line of work. To be clear, I think that line of work is fantastic. But there's this whole other line of work, which is to say, let's actually take these tools and incorporate them into the networks that we're using to make them sometimes more complex than networks, but able to capture things that are very hard for modern networks to do. So actually able to expand the power of deep networks by using the tools from optimization and from control. And I think that that's actually a very powerful paradigm, and I think we're just getting started on it to a certain extent. And if you're interested in that, by all means, come talk with me. And papers and code are of course available on my website. Thanks very much.